Is that better? Ask her if she can hear me now. Oh, that's pretty loud too. Sorry, let me turn the, oh my God. See, I do that like half the time. Thank you. I'm glad someone was there to, thank you, Frankie. Okay, so that was just blank for a while, but anyways, so like I said, we'll talk about volumes by slicing and then go up to the lab for the second half of class and do this lab. Yeah, so how are those videos? Do they seem fine? I really like the word sliver. I was thinking of, cut these things and you get these little slivers and then you basically approximate them with cylinders. And then you can find the volume of, some nice objects. You'll really learn how to do volumes in multivariable calculus. You can do more general volumes, but anything where the slices are nice enough that you can find the area of the slice at a certain height, you can actually find the volume of just by slicing. So did the cone example make sense? That used similar triangles, right? And I think I tried to draw carefully what the triangles were. I wanted to do the sphere example, which I provided a video. I did do a video for, but I didn't want to make you watch too many videos. So I figured I would just do it together so we can discuss it. And if you already watched it, you can feel smart, which is a nice feeling in a math class. So, okay. Volumes by slicing. So let's just do an example of a sphere. I don't remember what radius I used in the video. Doesn't really matter. Let's just say radius. Let's say radius 3. Why not? Okay, so if I wanted to find, so you might have already known. You all know the formula for the area of a circle of radius r. Did people know the formula for the volume of a sphere? How many people thought they knew the formula for the volume of a sphere of radius r? No one? Maybe? Good, we're gonna figure it out. That's nice. Okay. So so I'm gonna use the number 3 here, maybe 5. You know what? There's some 3s that float around in the problem, so let's use a number that's not, because I want to see how this generalizes if I replace 5 with like radius a or something. Okay, so the idea is you draw this sphere, and this is the radius 5, and I think the thing I tried to impress upon you in the videos was that you want to coordinatize the situation. That's like the first thing you want to do is like draw an axis somewhere and decide where like height 0 is, because we're going to slice this into these little slivers that are all these little cylinders, or that we can approximate with cylinders. And so you need to like decide what, I could make y equals 0 at the bottom here. The top would be what then? What height would the top be if the bottom was 0? 10, right? Because two radii make a diameter. So it'd be height 10. So I could go from 0 to 10 if I wanted to. But because of the symmetry of the sphere, it's nice to actually put height 0 right in the middle, like the equator, So you draw an axis. Let's call it a y-axis, and let's put y equals 0 right there. And then that means this is y equals 5 up here, right? And y equals -5 down here. And some people like just finding the volume of like the top half of the sphere and just doubling it or something, but we'll actually do some stuff next week with densities, and where like the density could be changing and you can't necessarily just double your answer, do half of it and double your answer, because if like we could find the mass of an object, and if the density of the bottom half is more than the density of the top half or something, then you wouldn't just be able to find half and double it, because there'd be more mass in the bottom half. So for volumes, you can do that. You can get away with that. But I might do this fully in general, just not to worry about that, not to have to just to prepare us for other situations. And then you take one of these slices, right? And so if this is height y, then the slice at height y is a circle, right, of radius. Well, it depends on y, depending on the height. Right, what's the height? If y is 0, what's the radius of the circle? The slice at height 0. 5, what about at height 5? What's the radius of the slice? 0, so it's actually kind of almost not a slice, right? The slices get tinier and tinier. At the top, it becomes 0. At the bottom, it becomes 0. And so we want some formula for the radius depending on y. But it has to match, it has to like agree with those. Like when we plug in 0, we should get 5. When we plug in 5 or -5, we should get 0. It's a little harder if I ask you what the radius is if it was at height 3. It's a little bit harder. But that's the idea, is we want to figure out like what the radius of one of these circles is. And actually, let's do an example. Well, let me actually call this R. So that's radius R. But R is going to depend on y. Let's do an example like height y equals 3. What's the radius of the slice? And what I sort of said was, with the cone example, and you can kind of do the same thing here, is you can kind of try to flatten it into like a 2D side view. That makes life a little easier. Like we're kind of looking at a side view of the sphere here, but you can also do it, I kind of like flatten out. And if I want to think about what the side view is, or like if I shone a light, shone, shined, shone a word, shone a light, can I shone a light? If I shined a light, I think I just made up the word shone. If I shined a light on the sphere from the side, what would its shadow be? It'd be a circle also, right? Although it's a different circle now. It's like a vertical cross section, kind of the vertical. So the side view is just this, but we can sort of label something. That's supposed to be a circle. We can label some things, right? Like that's 5. And if we took the slice at height, I mean, I can draw this axis again. This axis is still in the picture. First thing you do is draw, is like pick an axis. So 0, 5, -5. Let's look at height 3. So the side view of a circle is you just see the diameter, right? So let me just draw a radius. So that's a radius of the circle, and that's our R that we want to find, right? And the question is, can you find that length just given the information here in the picture? I mean, it does have some length, right? It has some specific length between 0 and 5. Well, let me start drawing some stuff in here. So this is 3, right? What else could I draw in this picture? I want to know what R is. If you watch the video, the third video, you might know, but yeah. From here to there. That's also a radius, right? It's a circle. This whole thing is radius 5. So that also is a radius. And now we have something nice, right? I think, do you believe now you could figure out what R is? Yeah, actually, you know your Pythagorean triples. It's 4, right? Good. So, but in general, like R, right, is, we have, yeah, from Pythagoras, we have 3 squared plus R squared equals 5 squared. And so in fact, that means R is 4. So that's the radius of the slice at height 5. And then the area, so then I mean, not height, at height 3, sorry, I think I just height 5, I would say height 3. So that's the radius of the slice at height 3. So the area of the slice at height 3, since it's a circle, is, remember, I'm going to use this A of y for the, in fact, I should probably say this, like A of y is the area of the slice at height y. And that's what we're going to, that's the function we're going to end up integrating, right? You've seen from the examples that we've done so far. So that's A of 3, which is pi times 4 squared. So it has to be 16 pi here. Is that plausible? So here, so it's funny with the cones, I mean, there's some, you sort of learn the methodology, right? With cones, you end up using similar triangles. With spheres, you end up using the Pythagorean theorem. That's the governing geometry. And so in general, if we generalize this, and we're going to get something like the following, right? If I just want this, maybe I'll even do it on this picture, but just like down here or something. If we just picked a random y, sorry, being lazy and drawing on the same picture, but let me do it down here maybe. So that's a negative y, I guess, which we have to be a little bit careful about, but then this is the radius we would care about, right? And then, but we can draw in this right triangle right here. We know this is 5. We know this is, I guess it's really like absolute value of y, if I wanted to be. But we're going to square it anyways when we do the Pythagorean theorem, so it doesn't really matter. And this is r, in this case. And so we get y squared plus r squared equals 5 squared. And so r squared is 25 minus y squared. And then r is the square root of 25 minus y squared. Right? And so that's the radius at height y. You just solve for, you just use Pythagorean theorem and solve for r. Does that work when y is 0? Does it give us what we expected when y is 0? Yeah, right. Square root of 25 is 5. That's the radius of the slice at height 0. Does it work for heights 5 and -5? Yeah, if we plug in 5 or -5 here, we get 25 when we square it. So we get radius 0. So that's a nice thing to check. Okay, and then actually, then A of y is pi r squared. So we didn't even really need the square root. So it's pi times 25 minus y squared. Okay. And now that's what we're going to integrate, right? The volume, remember, is the integral. It's going to be, where are all the slices? The slices go from -5 to 5. Below -5, above 5, there's no slices anymore. So we just integrate from -5 to 5. Yeah. So the volume is the integral from -5 to 5, A of y dy, which in this case is the integral from -5 to 5 of pi times 25 minus y squared dy. So maybe take a few minutes, talk to the people next to you and just work this out, this integral. See what this is something you should be able to do by hand without too much trouble. So yeah, chat with your friends. I'll let you guys do that for a minute. I'll check the chat in case anyone remote has a question or anything. Hopefully you can see the board. You might also think, if you do finish this, about how to generalize this to just a sphere of radius. I'm scared to say R because we're already using the letter R. You could do capital R instead of lowercase r. But yeah. This is working out. The negative 5 to 5 is a little bit annoying. I admit it's easier to do 0 to 5 and then double it. But let's be gluttons for punishment and do it the long way. What'd you get? Did you get the answer already?
No.
Or you're just chatting? Oh yeah, okay, that's great.
Okay.
Shouldn't be too bad, right? The hard part's really the plugging in the endpoints, I guess. Making sure you have all your minus signs correct. So first thing probably resolve is all the minus signs. You know, you can get all these numbers. I think I was trying to be fancy in the video, and I think I used 5 actually in the video because I think I remember doing this with like, it's 25 times 5. You can think of it as 125, or you can think of it as 5 cubed. All right. So that becomes minus, I guess, I get a plus. I have to be really careful here, right? All the minus signs. Here, there's 2 minus signs, so I get a plus 5 cubed. And here, there's 1, 2, 3, 4, 5 minus signs. You want to think of it that way? So that's a minus 1/3 5 cubed. Yeah, and then again, you can write this out, but I like to try to be fancy and say, well, I could actually pull out a 5 cubed here and get 1 minus 1/3 plus 1 minus 1/3. I factor 5 cubed out of everything. Right, if I factor 5 cubed out of this, I have 1 left. If I factor 5 cubed out of this, I have a 1/3 left. And so that's 2 minus 2/3, which is 4/3. So it's pi times 5 cubed times 4/3, which is something like, I'm just gonna write that as 4/3 pi times 5 cubed, which turns out to be 500 pi over 3, I think. There's a cube around this sphere that's like 10 by 10 by 10 that would contain the sphere. So that would be volume 1000. So this should be less than 1000 if you, yeah, pi is a little bigger than 3, so pi over 3 is a little bigger than 1. So 500 times that's a little bigger than 500. So you fill up some percentage of that cube. But is that all believable? Okay, so any questions about any of the steps I did there? In my experience, students seem to be able to follow this, but then when I ask them to do it on their own, they have more trouble. So, not sure. One thing that's fun here is you can actually see the formula for the general. Like I really left the 5s separated. Like I didn't, that's why I kept them as 5 cubed, and I could have kept this as 5 squared. If you change the 5 to just the radius, like if you generalize, like what if we had radius, again, I also want to use like, maybe I'll use capital R. The sphere of radius capital R, just because I'm already using a lowercase r. All the 5s in this would change to capital R's, right? So you could trace back through this computation again, and you would have like minus capital R to plus capital R here. These would all be capital R's. This would be a capital R squared. This would be a capital R squared. Sorry, I'm just kind of being a little bit lazy and not wanting to write out the whole thing, because it would take another like 15 minutes to write this out in general. That would be R squared. This would be R and R minus R to R. This would be R cubed. This would be R cubed. And this would be R cubed. And so actually, this is the volume for a general sphere. It's actually 4/3 pi R cubed. Has anybody seen that before? Look familiar now that you're actually seeing it? Yeah, so it's kind of nice. So you could have done this for a general, but this is kind of a famous formula, like if you want. It's a little bit weird. It makes sense that it's like pi and R cubed. It's a good analog for pi R squared, but then why is the 4/3 there? You can actually do the volume of a 4-dimensional sphere if you want. Very similar argument. And it's some constant times pi R to the 4th. Constant's escaping me right now. It might be 2. Is that right? 2 pi R to the 4th? I can't remember. It's kind of fun to try to think about volumes of an n-dimensional sphere. That's how I spend my weekends. I don't know about you, but that's what I do. Okay, so any questions about that? Yeah.
So if we, sorry, if we know the volume of like any sphere, we can just use that, integrate that between bounds.
Well, if you want to know the volume of any sphere, you can use this formula. But if I want you to show me that you know how to do the slices, you have to kind of set it up this way and do it.
Can we just use like the next step of the cheating one of the just a pi times r squared minus y squared?
I guess you could set it up fully in general and then plug in R, your radius R if you want, sure. Yeah, if you want to do it that way. Okay, so that's a sphere. And basically cones and spheres are the main sort of shapes that we do because they have nice slices. The slices are all the same shape. There's a section 8.2 is all about like the volumes of revolution with all the Washer and cylindrical shells methods. I don't want to do any of that crap. We're going to skip that. But we're going to move on to some other sections like 8.5 is like physical integrals, which is kind of interesting. Like I said, like mass and density, and you can do like work and stuff. And maybe it's like 8.5 and 8.6 or something. And then the last section of the chapter is on probability and distributions and stuff, which it's also nice to like learn about a little bit because we're living in a world where statistics and probability are more and more important. So, okay, I guess maybe I have time. The only other shape that we really see like that's not too bad because it's actually very similar to the cone is a pyramid. And so what about, so let's do one more example. Actually, let's do it with letters. Base width W and height H. Okay, so I want some pyramid like, you know, square, I guess I should say a square pyramid. Can I draw a square pyramid? Like that. It's kind of a square pyramid. And so the height is H. The base width is W. Because here, if you slice, what are all the slices? What is the shape of all the slices now? I guess I should say this is W also. So it's a square pyramid. So what's, I just said the word, the slices are all squares. Yeah, okay, good. So slices are squares. One reason I want to show you this example is I teased something in the cone video about like flipping it upside down, flipping the cone upside down, and that actually makes it a little bit easier. If you put the point at height 0. So let me try to do that. I claim that the integral works out a little bit more easily if you flip it over. So let's just do the side view. So I want something like this would be the side view, right? Just the shadow view if I flip it upside down. So here the slices are squares. And now if I want to put my axis on here, height Y, this is Y equals 0. This is Y equals H. And I guess a generic slice at height Y is like, has this, I use W for width. What other letter can I use for width? Should I just use X? Let's just call that X. So X is the width of the slice at height Y. Okay, like we said, this distance right here is W. And you know, we have a couple things here. We have like, this is height H, and this is height Y. So again, there's similar triangle nonsense here. You have this small triangle sitting inside the bigger triangle, and they're similar to each other. So I have a triangle. I should try to, let me see if I can be good and actually do these in different colors or something. So I have this orange triangle right here. And I have blue. The big triangle is blue. So I can draw a triangle. Sure, let's pretend that's like that. And this like this. And again, this is with X, this is height, whoa, Y. This is with W and height H. So can I get a relationship between X and Y? If you want to think specifically, this could be numbers. This could be like 7 and this could be like 10, you know. But I'm just deciding to try to do this fully general. So what do similar triangles tell me? Yeah.
W over H is equal to.
Yeah, right. The ratios are the same. Like W is to H is X is to Y. So similar. So W over H equals X over Y. I think I'm still on screen, hopefully. Oh, I just ran off the screen. I'm sorry. I'll write that again. I just wrote that last thing. I was off the screen. A video. Okay, so let me write that again. And then once we have this, we can integrate. And then we're going to get a nice formula, actually, which turns out to be something really interesting. It's kind of one other reason I wanted to do this, because this also works for cones. So yeah, we said W is to H as X is to Y. And we really want X as a function of Y, right? Want the width as a function of Y. So that means X is W over H times Y. Again, that should make sense at height 0. The width was 0. And at height H, the width was W. So if I plug in 0 here, I get X is 0. If I plug in H, the H's cancel and I get W. And then the area of the slice, since it's a square, is just X squared, right? No pi in this case, because the slice is a square, not a circle. And so that is W over H times Y all squared, which maybe I'll write as W squared over H squared times Y squared. And then the volume is the integral now from 0 to H, because those are where the slices are, of A of Y dy. Same idea. Now let me plug this in. And the W squared and the H squared are constants. So I can pull those out. Integral 0 to H of Y squared. And so we get 1/3 Y cubed from 0 to H, right? Again, sorry I'm using letters. You could do this with numbers, but I just want to see how this works out in full generality. This actually works out kind of nicely because the 0 just is 0 cubed. So this really just becomes 1/3 H cubed, right? So we get W squared over H squared times 1/3 H cubed. H's cancel. And the final volume is 1/3 W squared H. And that's really 1/3 base times height, if you think about it. So I know there's maybe a bunch of steps there, but it works out to be just 1/3 base times height. And that's actually true for cones also. Cones are 1/3 pi r squared H. So 1/3 the base pi r squared, if you give a cone of base radius r, 1/3 pi r squared H. And actually, I really think this is something interesting, like triangle, what's the area of a triangle? Someone tell me. 1/2 base times height. A triangle is something that starts off with a base and then tapers to a point in 2D. And the area ends up being half of the base times the height. Cones and pyramids are objects that start with a base and taper to a point in 3D. And the volume ends up being 1/3 base times height. This 3 is actually the dimension, it turns out. And if you did the same thing in 4 dimensions and you had an object in 4 dimensions that started off with something and tapered to a point, you'd actually get 1/4 of the base times the height. So it's kind of amazing, like this dimensionality, it's sort of, it came out here. I mean, it came from integrating the Y squared and getting a 1/3 Y cubed. That's where the 1/3 came from. You can find the area of a triangle in a very similar way, you know, like by taking horizontal slices and you end up having some function that's linear. And so when you square it, when you integrate it, you get 1/2 Y squared, and that's where the 1/2 comes from in the area formula for a triangle. So it's kind of funny. It's just, I think that's kind of a cool thing, like just a cool thing to notice, like the 1/3 there is actually anytime you have a cone or a pyramid or anything that just tapers to a point nicely in 3D. That works. Okay. Cool. Any questions about anything? But notice, by the way, when we flip this over, we could have done this with the cone too, and we got a pretty easier integral. Remember with the cone example, this was like 5 minus y or something, like height minus y, and then you got something uglier, and I foiled it out and in the cone video and did everything. And here you can avoid all that just by flipping it over. This is a nicer expression. We get a nicer relationship between the height and the width, or the height and the radius or whatever. So that actually works out nicely too. Okay. Fair enough. All right, let's take a break. Reconvene upstairs in 5 minutes. And there's lab that's just like a fun exploration, just like click around Mathematica and do stuff that we can start playing around with for like a good 35 minutes or so. Okay. And for, I'm gonna end up stopping the recording and then just stopping the Zoom, but you can go to you're gonna go to the handouts page. Actually, if I show you the screen, can you see that? There's this calculus and Mathematica notebook that you can click and download and open. If you go to the handouts page on our webpage, there's a handout for today. And so if you're at home, you can do that also. You can just download it. Oh, I don't know if you have access to Mathematica, but this is more just a fun lab. So, all right. So let's break. I'm gonna stop. Yes.